Alright, our Forces 2 worksheet. M3, M4 hanging off the side of the table. If you're not on a surface, you don't have force normal. Looking at the free body diagrams, two of them have a force normal. That'd be M1 and M2, so we can label those in. The difference is M2 has tension on both sides. For the other two, M3 has tension up and down, where M4 only has tension up. I'm just looking at where things are connected in the diagram. A man pushes on a 12-kilogram object for 10 seconds. It moves 8 meters to the right. Calculate the acceleration. Sounds like kinematics, if I'm going to be honest. V0 is 0. Delta x is 8 meters. Time is 10 seconds. We're looking for the calculate the acceleration. Based on the information I'm given, I'm tempted to use delta x is equal to v0 t plus 1/2 at squared. v0 t is 0 because v0 is 0, so that goes away. Multiply both sides by 2, divide by t squared, that'll solve for a. I prefer decimals over fractions, so let's try to always use the decimal answer. 0.16 meters per second squared. Now we're going to use F equals ma to calculate the magnitude of the man's force. So if the mass is 12 and the acceleration is 0.16, we can calculate their force. I'm sorry, 1.92 newtons. If the surface is frictionless, how does V3 compare to V2? So once he lets go of it, the net force horizontally is 0. There's nothing acting on either side, so the velocity will be maintained. V2 is equal to V3. When you're looking at the forces parallel to the direction of motion, if the forces are balanced, we have constant velocity. There's no reason it would speed up or slow down. Now, if the surface has friction, when he lets go of it at the end of V2, on its way to V3, it's no longer balanced. You have a force that's opposing the motion, and your net force would be in that direction. The acceleration would be in that direction. So it would be slowing down. That means V3 is less than V2 or V2 is greater than V3 because you do have a net force. The net force is in the opposite direction of motion. Therefore, the acceleration is in the opposite direction of motion. Net force would be to the left, acceleration would be to the left. Object slows down. V2 greater than V3. Now it tells us that there are contact forces. We've said in our classroom, we have contact forces and field forces. Field force is the only one we're going to study is force of gravity. So electrostatic is also another one, but we'll set it aside for right now. That means our objects, to have a force applied to them other than gravity, it has to be touching. Tension, contact, normal, contact, cause acceleration, both. Gravity field, electrostatic field. Now it's just saying we're looking for the Newton's third law, action-reaction force pairs. So that means two objects. You can't go outside the two objects. Force opposes normal force pushing up on a box. So if the counter is pushing up on a box, the box pushes down on the counter or on the table or whatever. Action-reaction force pairs. Don't bring gravity into this because gravity is a third party. Also gravity's field and normal's contact. For B, what force opposes the force of weight pulling down on the box? The weight pulling down on the box is the earth pulling down on the box. So the reaction, the force pair, the box pulls up on the earth. And I'm just saying here, pulls back on the earth because the earth is the source of gravity. Okay, a couple guys pulling on a box. Looks like there's friction sitting on a floor. So when you pull the rope, that's tension. Pushing up by the floor, normal. Pulling down on the mass, gravity. Trying to resist the motion, friction. Negative in the x direction, friction. Positive in the y direction, normal. Positive in the x direction, tension, because to the right and up are positive. And then negative in the y, gravity. Which forces would be used in the equation summation of forces in the y? Force normal and force gravity. Which forces would be used in the equation net force in the x? Force tension and force of friction. Two masses are attached by a rope, threaded through a pulley. Identify the four forces. Okay, we've got tension, gravity, and normal. There's no normal, so that won't be an answer. F1, that's gravity. F2, tension. F3, tension. F4, gravity. Which two forces are equal? F2 and F3. You have a single rope. It's not interrupted by any mass. So one rope, one tension. Calculate F1. F1's a force of gravity for the 2 kilogram mass. 2 kilograms times 10 gets you force of gravity of 20. Calculate F4. That's the force of gravity on the 8 kilogram mass, so 80. Which forces are in the y direction? They're all in the y direction. Which are in the x? None. Which way the system accelerate? It's going to go, 2 is going up, 8 is going down. So in the direction of the 8 kilogram mass. Which force is bigger, 2 or 1? It'd have to be 2. If the 2 kilogram mass is going up, accelerating up, F2 has to be bigger than F1. So for the next question, the y is the direction of the acceleration. The net force follows the direction of the acceleration. Which force is bigger, F3 or F4? Has to be F4. The 8 kilogram mass is accelerating downward. In order for it to accelerate downward, the net force has to be down. F4 has to be bigger than F3. Find the acceleration of the system. Use your big freaking object. Total mass in the middle, 10. Being pulled to the right, 80. Pulled to the left, 20. Tension's internal. It does not affect the system. So net force, 80 minus 20 over the mass of 10 gets you the acceleration. We only used external forces. So 60 divided by 10, or 6 meters per second square. So a small child standing on a scale in an elevator. Elevator's moving at a constant velocity. We don't care about the 14 meters per second. Constant velocity tells us everything we need. Constant velocity means balanced forces. If it's a 40 kilogram child, the force of gravity is 40 kilograms. Force normal is 40 kilograms. The normal force and the weight are the same. And they're the same because of constant velocity means balanced forces. The elevator is accelerating upward at 5 meters per second. The child didn't lose any mass, so the child has the same weight. Force of gravity is not changing. Force normal must have changed. Force normal is now increasing so that the net force is up. If the net force is up, the acceleration is up. So I'm showing here with the free body diagram, gravity is the same. Force normal got dramatically bigger in my drawing. Net force is up, so acceleration is up. So how do they compare? Net force is larger. Why? In order to accelerate upwards, we need a net force that's up. Gravity didn't get smaller. Force normal must have gotten bigger. The elevator is accelerating downward. Gravity did not get bigger. Force normal got way smaller. So gravity's the same. Normal's now smaller than gravity. Net force is down. Acceleration is down. How does normal force compare to weight? It's less. Why? In order to accelerate downward, you need a net force that's down. Since force of gravity is set by mass times the acceleration of gravity, in this case, force of gravity is not changing, weight's not changing. Force normal must have gotten smaller. Now for D, the acceleration is 10 meters per second square. We know that's the acceleration of gravity. If it's equal to the acceleration of gravity, that means there's no other net force acting on it. Or if there is, they're all balanced out, because the acceleration of 10 meters per second squared downward, that's free fall. So in this case, since there's only one other force, force normal, it is not reducing the net force from gravity at all. So force normal must be zero. If force normal is anything that was non-zero, since it opposes gravity, the acceleration would be something less than gravity. So here, force normal must be zero for the acceleration A to be equal to G, the acceleration of gravity, 10. Here I'm just showing that Fg is mg. And if it's mass times acceleration, and acceleration is g10, force normal must be zero for that equation to work. So explaining it to you in words, demonstrating it on the screen with mathematics. What is the acceleration of the following system? What's the tension in the string? One string, one tension. Now we can look at this and know that the 20 kilogram block is going down, 10 kilogram block is going up. Let's use our big freaking object, BFO. We put the total mass in the center. External forces, I usually do to the left and the right, showing that they oppose each other. To the left, 100 newtons. To the right, 200 newtons. In the center, total mass, 30 kilograms. Net force divided by mass is acceleration. 200 minus on 100 is 100. 100 divided by 30, 3.33 meters per second square. Now that we have the acceleration, we can symbolically cut the rope. Don't actually cut the rope. If you cut the rope, the system's broken. We're going to symbolically cut through and look at just one side. Force tension is up, force gravity is down. We're looking at just the 20 kilogram object that has an acceleration of 3.33. Since it's accelerating down, we do Fg minus Ft for our summation of forces. 200 minus Ft is equal to 20 times A. If you're doing the other side, it would be tension minus gravity because the 10 kilogram object is accelerating upward. So keep that in mind. Bigger minus smaller. 200 minus force tension is equal to 66.6. Let's subtract that 66.6 to the other side and add force of tension to the right. We get 133.4 is equal to force of tension. That's the same on both sides. Single cord, single rope, uninterrupted by a mass. We'll have the same tension on both sides. Last question, what is the acceleration of the following system? What's the tension in each string? Now we've got a string that's interrupted by a mass in the middle, so there'll be different tensions. We'll call it FT1, FT2. 12 kilogram mass has force gravity down 120. 20 kilogram mass down force gravity 200. The system will accelerate to the right based on this. Big freaking object, 32 kilogram mass in the middle. Oh, I'm sorry, I forgot the 5 kilograms in the top. All of the mass goes in at 12 plus 5 plus 20, 37. 120 to the left, 200 to the right. Net force is 200 minus 120. And we're going to divide by the total mass, 37. 80 divided by 37. .16 meters per second square. The entire system is accelerating with that value. So is each individual object. They move together. Force of tension 1, it's pulling up on that object. It is accelerating upwards. Tension minus gravity is equal to ma. Force tension 1 minus 120 is equal to 12 times 2.16. Multiply on the right and then add that 120 over because tension has to be bigger than gravity on the left. Force of tension equals 145.92 newtons. Now on the right, the 20 kilogram mass is accelerating downwards. So you can't always do tension first. Here we're going to say force of gravity minus tension because gravity is bigger is equal to ma. 200 minus force of tension 2 is equal to mass 20 times acceleration 2.16. We'll multiply the math on the right and then subtract it over to the left. And then we can add a force tension 2 to the right to set up our equation with the solution. 156.80 newtons is force of tension 2.